Hello and welcome to another Data Science Cornwall video. Today we're going to be looking at classifiers and looking at an interesting and useful way of visualizing classifiers in terms of their performance so that we can compare them. We're going to be looking at a technique called ROC curves, which are really useful but unfortunately not that well known for some reason. We're also going to be looking to see how we can actually improve the performance of individual classifiers by combining them, and ROC analysis really helps with that. But we'll start with just a quick review of the several ways of understanding performance, just to show that actually it's not quite as simple as a simple number. So here's the agenda for today. We're going to be looking at performance and ways of indicating it. We'll introduce this new idea of ROC curves and we'll see how we can use them to identify or optimize a classifier. And as a bonus at the end, we'll use a fairly recent technique for seeing how we can, almost by magic, invent a new kind of classifier which has better performance than what we had before. It's not really magic, but it's really kind of useful, and it's something I don't think many people know about, so we'll do that at the end. So let's start with a very simple scenario where we have a population of people. The green indicates that they're healthy and the red indicates that they are perhaps unwell with some disease, kind of topical right now. We have a classifier which is something that might be a neural network, it might be something entirely different. It doesn't actually matter. All that we are interested in it is how it behaves without having really to kind of know the ins and outs of what's happening inside this box. And the job of this classifier is to place these people either as healthy or unwell in these two classes, so one of the two classes. And here's something it can do. It can put 4 of those people into the healthy box, and like most real world classifiers, they're not perfect, so they do make mistakes. And we can see here this one has got an unwell person in the healthy box, so that's an error. Similarly, in the unwell box, in the unwell class, it has put some healthy people there. Now, how do we explain or indicate or write down a measure of this classifier's performance? Is it simply this proportion here, 4 out of 5? Seems reasonable because it's got 4 out of 5 right. It seems to be a good number. Does that paint the full picture? Actually, we might have a different problem on our hands where we care less about the healthy but more about the unwell, and maybe that's our focus. So maybe we should be focusing on this box and saying actually this performance is 3 out of 5. And if we do care about the unwell, what about this one that's left over here? So that suggests maybe that isn't the full picture. Maybe we want to again refocus on this healthy box, and our kind of primary driver is we don't want sick people being told they're healthy and walking around the population. So maybe we really need to care about the reds that appear in the green box. Maybe that should be our focus. So you can see from this really brief discussion that having just one simple measure that works for all scenarios isn't possible. So the message to take away there is we need to understand what problem that we are trying to solve, what we care about, what we need to focus on. And often one single number doesn't paint the full picture. Now, in many scenarios, we actually have a set of 4 numbers that are very useful. And they're grouped together, often presented in something, an array, a matrix called a confusion matrix. It's a funny name. I'm not sure the history behind it, but it's a fun name to remember. And the numbers that it summarizes are called the true positives, the false negatives, the true false positives and the true negatives. Now that sounds like a bit of a mumbo jumbo kind of bunch of words to remember, and when we first come across these ideas they're a little bit difficult to kind of quickly understand intuitively. So let's break it down. Along this row we have all the items, people that are actually well. We know this because when we train machine learning models, we train with data that we already understand. So we know there are actually 4 people that are well, or 6 people, and we can see that in the picture. But only 4 of those are classified well in this column, and 2 of them are mistakenly classified unwell. Similarly, we know there are 4 unwell people, and 1 of them is being classified well, and 3 unwell. So there's a good and a bad combination here. Coloured green are the correct answers. We know 4 of them are well and they've been classified well, and that's the true positive. We know that there are these 3 here are unwell and they have been classified unwell, which is good. We know that there are 2 who are actually unwell, but they've been classified as well as unwell, so they are not really negative. They should be positive. They're false negatives. They're actually well, but the classifier has said they're unwell, and these are these 2 sitting at the bottom here. And similarly, there's 1 unwell person who's mistakenly being classified as well, and that might have been the most the most dangerous or impactful error potentially, and that's a false positive. Now you can see our definition of what is positive and what is negative matters, and we have to kind of choose one that matches our domain, what we're trying to do, and keep consistent with that. We might say a positive is unwell. In this case we're sticking with positive is unwell, is healthy. Now based on those 4 really useful core numbers, the true positive, the false negative, the false positive and the true negative, people have come up with interesting combinations of those which are useful metrics, and they're not always ideal, but they are useful enough that they're in common circulation. So accuracy is sometimes, not always, but sometimes defined in this way. It's the green, the good answers, as a proportion of all the numbers, so the true positives and the true negatives as a proportion of all the other classifications. And obviously the higher these numbers are, the correct classifications, then the higher the accuracy. So in our model we had an accuracy of 0.7, which here is 7 divided by 10. And that's not bad. That kind of reflects the fact that looking across both of these boxes, 0.7 of them are in the right place. Another useful metric is recall, which is understanding of the ones that are actually well, how many did we find? So here we know there are 6 in total, but we only found 4. And that can be a useful measure of some classifiers, and it can be relevant in some cases. Precision is a different one, which is saying that of the ones we did classify as well, how many of them are actually well? And here we've got 4 out of 5, which is a fairly precise classifier. Not too bad. Could be better, but it's not too bad at 0.8. Now, those measures, it's useful to kind of develop an intuition with them by looking at extreme cases. By the way, don't worry if you don't intuitively understand them straight away. Most people don't. So here we've taken an extreme where a classifier has put most people in the unwell category, and it's only put 1 person in the healthy category, and it's a correct person. This person is actually well and healthy, so it's not wrong, but actually it's missed all these. So here we have a recall that's very low, because it's missed lots of positive examples. They're all in the wrong box. But of the ones it did catch, it didn't get any wrong, so the precision here is perfect, it's 1. So you can see now how recall and precision work. Recall precision is really high, but unfortunately recall isn't. Here's another extreme example where we've put everyone into healthy box. It's almost like this classifier didn't do any work at all, it just threw everyone in healthy. It'd be interesting to see what recall and precision look like here. So here recall is perfect because it's caught everyone that should be in there, but precision is really poor because there are people in this healthy box that shouldn't be there. So you can see again this interplay between recall and precision. And they're useful kind of measures to kind of think about, and they summarise different aspects of a classifier. And we could stop there and say, right, that's enough for today's kind of talk on understanding and measuring and explaining, communicating how well a classifier behaves. But let's carry on because there's more we can do here. Now these matrices, these confusion matrices, are really useful because they summarise all of those useful numbers, the true positives, the false negatives and so on. And if you want to compare several classifiers, we don't really want to be staring at lots and lots of these matrices. It's not very easy. It's not very, for our human brains, it's not very easy to kind of look at a grid of numbers and understand relatively which ones are better than others. And that's where ROC curves come in. ROC is a term that means receiver operator characteristics, and it's a term that comes from, I think it's the Second World War, where it was applied to radar detection of enemy aircraft. That's where it comes from, but it's not how it's used today. So a ROC curve, or ROC space, is where we plot the performance of a classifier by plotting the true positive rate against the false positive rate. Now there are other combinations that could have been chosen, true positive against true negative, for example. But these are the ones that have emerged through history. They're equivalent in some sense, but this is the one that has become the convention. Now, just worth noting that when we say rate, it's the total true positives divided by the actual positives, so it's a fraction. So it's not going to be a number above 1. That's why the axes go from 0 to 1. So if we look at this example here, so here the rate will be 4 out of 6. So again, using extremes to develop an intuition is sometimes a good thing to do. So let's see where a terrible classifier will sit on this ROC square. So this classifier classifies everything negative. It doesn't do any real work. It's just lazy. Because it classifies everything negative, there won't be any positives. So it has no false positives, which sounds good. But because everything's negative, there won't be any true positives either. So it's at 0, 0. It's useless. Let's look at another one. This one classifies everything positive. Again, it doesn't do any work. It has not really been trained. It's just lazily dumping everything into the positive box. So it has a 100% true positive rate, but actually there are things in that positive box which shouldn't be there. In fact, all of them are there. So it has a 100% false positive rate as well, which is why it's in the top right hand corner. And there's a pattern here which we'll come to. Now, a perfect classifier has 100% true positives and 0 false positives. Very rarely that we get that, but that would be in the top left corner. 100% true positives and 0 false positives. So that's the ideal corner that we are aiming for. We're rarely going to get there, but that's the direction we want to configure and train towards. And let's look at another classifier where, again, it's not really being trained, it's not really doing any useful work. What it's doing, it's randomly assigning positive 50% of the time. So every time it sees a data instance, half the time it says, yep, you're positive, without really thinking about it or applying any knowledge. So it's a random classifier which for 50% of examples classifies them as positive. So it has a 50% true positive rate, because it's going to get half of them right, but actually half of them shouldn't be there, so there's a 50% false positive rate as well. So it's in the middle. And actually this line is interesting, because if we had a classifier that randomly assigned positive, 80% of the time it would sit here, 80% true positive but 80% false positive. Similarly, this one does it 30% of the time. So we can see that everything along this line is useless. It's randomly classifying, or as good as randomly classifying. And if we have a classifier that sits anywhere along this line, it's not a good classifier at all. So we want to be away from that line in this direction. So we want to move classifiers away from this line towards this ideal corner. And why do we say this direction? Because this direction means a lower false positive rate moving left and a higher true positive rate moving up. So moving left is okay, moving up is good, doing both is better. And these are the previous examples that we looked at, plotted on this ROC space, this ROC curve. It's not curve yet, it's points in ROC space. So this one that we came across, the stupid classifier, does sit in this top right corner along this line, so we can see it's useless. This one wasn't quite so bad, it got one right, but it's very close to this bottom left corner and close to this line. So you can see just by looking at it visually, it's not a good classifier. Whereas this one at the start was fairly okay. You remember it had an accuracy of 0.7, so it sits around here. So it has a true positive rate of 4 out of 6, so it's 2/3 up and a quarter across. So good, worst, and this one's pretty bad. Now, an interesting question that's sometimes asked is, can we have a point beneath this line? Well, you could. You could have a very high true positive rate and a low true positive, sorry, very low true positive and very high false positive rate. But to be there, it's not acting randomly, it's actually using some information to move away from this line. So all that classifier needs to do is use that information differently and move this point up here. So it's got information about the data, useful information, but applied it wrong. So it's not random. So we just need to flip the logic and put the points there. But you're rarely going to see that. It's just kind of a logical kind of point there. So let's now turn towards a really useful application of this ROC space, which helps us tune classifiers. So let's go back to our example earlier of this classifier, which classifies people as healthy or unwell. And this time let's imagine there's some parameter that we can tune. And like I said earlier, we don't have to have, kind of a decision tree or a linear kind of classifier or linear regression or neural network or something fancy. We don't have to say what it is. So this can be a classifier in abstract, but we have some control that we can adjust to change how this parameter, this classifier behaves. So if this dial is turned this way, it might behave like this, where we have a small number of good results in the healthy box and everything else is over here. And if we tune it, we might have a different outcome. Not always good. Now, if we plot, if we work out those confusion matrices for every kind of configuration of that parameter, that tunable, we can plot the different matrices, the true positive rates and the false positive rates in this ROC space. And we can connect those dots and we have a ROC curve. And almost always these will be convex, not always, but in most cases it'll be convex. Now you can see that when at one extreme it's going to be a pretty poor classifier, and at the other extreme it'll be pretty poor as well. So often there is some kind of middle ground, and it's the one which is closest to this ideal point. And here we can see that it's this configuration. Whatever we dial this parameter to, this knob, this is the one that seems to have quite a good true positive rate and not such a bad false positive rate. If we dial it up, we might be able to increase true positives, but the false positives go up as well. So this seems to be some kind of optimal, and this is a great way of visualizing and then choosing a good configuration for a classifier. There's more to it than that, but we'll come back to that later. So you can see immediately that this plotting of classifier's performance in ROC space is really, really helpful. Immediately we can just look at that and say, yep, that's the one that we want. Now, not every classifier has this kind of tunable. Sometimes it just gives a yes or a no, or a class A and class B, class 1, class 2. We can still use ROC analysis in those cases as well, if we can have some kind of score or probability for the outputs. So you'll know that many in fact, models produce an answer with some kind of score or probability. So a neural network will have output values that often range between 0 and 1. And we can interpret them as probabilities, for example. Now the way to do that is, we here have known actual classes for the data, because this is training data. We score, we look at the scores and we organize this table in descending order. So this data, it does have an actual class of positive, and it was assigned a score with a probability of 0.99, so very certain. Don't know what that score is yet, but that doesn't matter actually. And here near the bottom of the table, the score that was given was quite moderate at 0.55, so fairly uncertain. And what we can do is we can adjust a threshold and say, if we have a threshold of 0.95, everything above that threshold is going to be positive, and everything below that threshold is negative. So we're saying this threshold controls the difference between positive and negative outcomes. So here we have two positives, we've said, because they're above the threshold, and all these we're going to say are predicted negative. Now we know not all of them are negative because we know the actual class, so we can build a matrix again of false negatives, true positives, and so on, and plot them on a ROC square like this, and we can adjust the threshold and do it again. We can adjust the threshold and move all the way down, and you'll see that as we adjust the threshold, the performance of this classifier changes, and we can see again this kind of convex shape of, it won't always be convex, but often is. So we can see that the best configuration for this classifier is going to be whichever threshold gave us this point here, because the true positive rate is fairly high and the false positives aren't too high. So that's another way of using this ROC analysis. Now, something worth mentioning is the area under the curve. It's used a lot in the literature, the books, the papers, as a way of summarising how good a classifier is by looking at the area under this curve. And you can see that the higher this curve, closer towards this ideal point, the higher the area is going to be, the larger the area. Now, it's a rough and ready measure. You can see it kind of works, so we can look at this and say, yep, this curve, this classifier is better than this one. It's always higher and closer towards this ideal point. Now that's a good kind of single number that represents how good a classifier is, but as we said at the start, single numbers can often be deceptive, and there are cases where that falls down. So the AUC, the area under the curve, can be overly simplistic. So the area under this purple pink curve is higher than the green one. However, this green one does perform better in this region. We can see it's closer to this ideal point. Its true positives are higher and its false positives are not too high at all. So just be wary of that. Now another good question that's asked is, well, we've formed these confusion matrices and we've plotted these ROC points, these ROC curves. Does the skew or an imbalance in the training data between positive and negative classes matter? And the answer is it doesn't for the purposes of ROC analysis. Let's see why. So here's the same data that we had before, and we've got true positives at 4 here and false negatives 2. So we have a true positive rate of 4 out of 6, which is 2/3, and a false positive rate of 1 out of 4, which is 1/4. Now let's double the number of healthy people in this population. Now when we do that, remember the classifier is still going to treat them in the same way, which means it'll put the same proportion in the healthy box and the same proportion in the unwell box as it did before. That doesn't change. Simply by changing the population, the classifier itself doesn't change. So let's double that. So we now have got, so you can see here we had a total of 6 actually healthy people and 4 unwell, and now we've got 12 and 4 unwell, so we've doubled the number of green people, and our true positives are 8, false negatives 4, and the numbers, if we do the calculations again, match up again. 8 out of 12 is 2/3, false positive rate 1 out of 4, which is 1/4. So this method of ROC analysis is not sensitive to imbalances in the population or the data set between each class, and that's because we're looking at rates rather than absolute values. So that's nice. That's a really nice property. It also means we can look at comparing classifiers which were tested on different data sets with different balances of healthy and unwell, or just different class kind of proportions. That's a really nice strong property. So let's revisit this question of best classifier, because I guess some of you thought the earlier discussion was a bit simplistic. Let's challenge ourselves with this example. Now ask ourselves, which of these is better? They both seem to kind of rise and be kind of fairly equidistant from this ideal point. Which is better? Now what you can see is this one has a lower true positive rate, but actually has overall lower false positives in this area. This one has a higher true positive rate, but the downside of that is it has a higher false positive rate as well. So like everything in life, there's no free lunch. We can choose this one, which is more conservative. It gets a good amount right, but it doesn't get many wrong, whereas this one does get more right, but it does get more wrong as well. There you can see higher true positives and lower false positives here. So we have to decide at some point which we care about, and that will depend on the problem you're trying to solve. So you might say for some problems they're equal, don't really mind, but in other domains, in other scenarios, a false positive might be really dangerous. So you might say we really don't want people being told they are healthy when they're not, particularly if they've got a very infectious disease. Let's look again at that idea and refine it a little bit more. Now here we've got a very simple ROC curve for a classifier, and this point we've previously said is the best point. Now the cost of false positives, as in we don't want false positives, so they have a cost associated with them. If the cost of a false positive is the same as the cost of a false negative, what we do is we choose this line with gradient 1 and we kind of move it down from here, like I'm doing with the pointer, until it touches the curve. And that's what we've been doing up to this point. It's very simple, kind of works, but it's made the assumption that the cost of a false positive is the same as the cost of a false negative. Now, we don't want any of these ideally, but we're going to get them. Now let's think about what happens if the cost of false positives is higher. So we definitely don't want false positives. We don't mind false negatives. We don't mind, say for example, people being told that they have an illness when they don't, in a particular scenario. But we really don't want to tell them that they're healthy when they're not, because they might spread a disease or not treat it. So here now we've said the cost of a false positive, let's say it's double. Now intuitively we want to be more conservative then. We want a lower false positive rate because that's what costs us more, so we move in the left direction. Now I won't do the maths here, but if you wanted to look it up, I've linked the references. You'll see that this gradient here now becomes 2. So we move a line with gradient 2 until it touches this ROC curve, and we can see that it touches it at a point with lower false positives, which is what we wanted, and unfortunately lower true positive rate. It's a more conservative, more cautious classifier, and that takes into account this point of the false positives being twice as expensive or costly as the false negatives. We can do the inverse as well. We can say actually the cost of a false positive is half the cost of a false negative. We might want to avoid false negatives, and here the gradient then is a half, if that's the ratio. And then you can see intuitively it's correct, it moves more to the right. We can afford more false positives because they don't cost us so much, and we can increase our true positive rate. Now if you wanted to dig into the maths of that even more and think a little bit about actually if the cost of a false negative or a true false positive matters, then actually we do need to care about class proportions, because if I have a population with many say negatives, there will be more of those in absolute terms. So the maths turns out to have 2 ratios. Previously we used the ratio of the cost of the false positives and the cost of the false negatives to inform the gradient, and now we have negative over positive. So the number of negatives, the number of positives in the population. Now let's look again at this promise that we made earlier about seeing if we can do better than the classifier that we have at hand. Now here we've got 2 classifiers, a pink one and a green one, and imagine that we actually wanted a classifier that operated in this space, so higher true positive than this one, but not up here where the false positive rate is really high, so somewhere in between. That would be nice. Now, is there a way of combining these that gives us this? And the answer, it turns out, is yes. And that's actually an easy thing to say, but quite powerful in its kind of usefulness. And you can read about it. It's a fairly recent paper actually, so it's a fairly recent discovery in some sense. Mr. Scott, he proved that if you combine classifier and B, you can invent a new classifier. You can kind of create one from these 2, which can operate anywhere along this line between the 2. So if I've got A which has this kind of behaviour and performance, and this one B up here, I can have any classifier as long as it sits somewhere along this line. So I can choose how I want this new classifier to behave. The only constraint is it has to be somewhere between the 2. And that's done by randomly using A and B, but in proportion to how far along this curve we want. So if we always chose A, we'd be here. If we always chose B, we'd be here. If we chose A and B half the time, when we're kind of analysing data and making a decision about it, we'd be halfway between the two. And if we wanted to be here, we'd use A 3 times as often as, say, B. Now that makes intuitive sense, but it works mathematically as well. The only thing we can't do is move away from this line in the better direction, because there's no free lunch. There is a theorem actually in machine learning books which is often termed the no free lunch theorem. So we can't get something for free, but we can combine things like this. So this is just illustrating this classifier C, which is actually A and B being used 50% of the time each. So that's quite nice. Now let's finally look at a really challenging example. Now imagine we have a linear classifier which simply draws kind of a line between data points to make a decision about whether they're positive or negative, class 1 or class 2. This data, so if there's a kind of a feature like height or blood sugar level or something that's along this axis, normally if we just had, say, these two here, just these two peaks, we could draw a line here and say to the right of this threshold we have class 2, and to the left we have class 1, and it would be very good. You know, you wouldn't get everything right because some of class 1 leaks across the threshold and some of class 2 leaks across threshold to the left, and most kind of classification scenarios do that. They're the source of the false negatives and the false positives. Now if we have data where there are 2 peaks, we're actually using the wrong classifier, because one linear classifier that draws one line, one threshold, isn't the ideal thing to do. But imagine that we were stuck with that situation. What we would end up with, well, the question is, where do we place this threshold? So if we placed it here, class 1 here would be right here, but this data for class 1 would be wrong. We're saying everything to the left is class 1 and everything to the right is class 2. So this is correct, but everything else is, this one is wrong, but the green ones would be correct. If we placed it in the middle, we'd be half right and half wrong. And if we placed it here, we'd be correct for all of class 1, but wrong for half class 2, because some of it's on the left. Now this is taken from Scott's paper, so the credit goes there. This is the ROC curve that will be produced for that linear classifier, because as we move the threshold, we start by improving our, let's look at it, we move along this direction. We start by improving our classification for class 1. There you go, it's improving. But then we don't improve, and we actually gain false positives along here, because these are, if we move from here towards here, these are now being classed as class 1 and they're not the class 2. And the same kind of thing happens here. So you can see there's these 2 peaks. Now this is a terrible curve. We want to be up here somewhere. What can we do? Well, what we can do is we can take a configuration of the classifier here and another one here and use that theorem that Scott proved to interpolate between these 2 points and come up with something that's here, like this. So we pick a configuration A, configuration B, and by combining them we can come up with classifiers that are along here. And this is a plot from his paper where he shows this done experimentally, which is why it's a little bit jaggedy, because it's based on real data. So that's really cool. It sounds like magic, it feels like magic, but it isn't actually. It's we've not gained anything that we shouldn't have gained, but we have taken advantage of these 2 good points to kind of find a better area here. Now if that doesn't sound believable, let's work through the numbers to see how they kind of emerge. So let's look at an example where we have just this classifier configured at A, and it's everything to the left of it, of the threshold, is classified as positive, and everything to the right is negative. Now for simplicity, we're just going to have one data item in each of these classes, so 1, 2, 3, 4 items. So there are total 2 positives in real life and 2 negatives. Now with this classifier, we've got 1 right and 1 wrong, because this class 1 to the left is right, but this class 1 to the right of the threshold shouldn't be there. It's being classified as negative. Similarly with the negatives, they're all class 2s, they're all to the right. So we end up with these numbers. These are count marks, not 11, that's 2. And we have a true positive rate of 1/2 and a false positive rate of 0. And that was the point on the... It was around here, so because we're using simplified data, it's going to be here 0.5, 0. Now if we move the threshold to the right here, we're going to have all the class 1s correctly classified and not have any errors there, but for the class 2s we're going to have 1 right and 1 wrong, so we have a different set of numbers here. And if we calculate the true positive rate, we do have a true positive rate of 1 for the first class, and we have a false positive rate of 1/2. And on the chart, so that's about here, so that's kind of where we had on the chart before, so 0.51 and 1.5. Now what happens if we actually combine those numbers? So we did A and B, so we have the scores that we had for classifier A, scores for classifier B, and we added them together. We kind of used both. So you can see now we've got 3 that were actually class 1 classified as class 1. And if we continue through, now we've doubled the totals because we've run through the data twice, you find that the true positive rate is 3 out of 4 and the false positive rate is 1 out of 4, and that ends up being here. So the numbers do work out. Fantastic. So just to kind of summarise, ROC curves and ROC analysis is useful. It's I don't know why it's not that well known. Simplistically, they're a very visual way of seeing and comparing and understanding the behaviour of a classifier, either different classifiers or one classifier with a configuration being changed, like a threshold or some parameter. They're useful because you can compare different kinds of classifiers. You can compare, say, a decision tree with a linear regression model with perhaps a neural network. You can have different data behind each of those classifiers because the population skew or kind of imbalance doesn't matter. It's the rates we're looking at, so it's a good way for taking that into account. Most usefully, and how they're really used in real life, is to find optimal points on a classifier, either simply or by taking into account relative costs for false negatives and false positives. We've said the important point that class imbalance is not really a problem, but we do take it into account if we are concerned about relative costs. And finally was the really nice bonus of being able to combine classifiers to get what could be for us a better classifier, and that's a relatively recent kind of development and has kind of solid maths behind it. So I hope you've enjoyed that. We'll see you next time. Bye.